welcome to everybody for this new session of our DinAmicI seminar. So today is a special seminar. We have not one, but even two very distinguished speakers, Daniel Peralta-Salas from ICMAT in Madrid and Eva Miranda from UPC in Barcelona, that are going to give an experimental two-body seminar. So the title of the talk will be looking at Euler flows through a contact mirror, Universality and Turing completeness. So before starting, let me just remind everybody that this talk is streamed online. So if you don't agree to be recorded, just switch off your camera and mute your microphone. And if you want to ask questions, just feel free to unmute yourself and ask it directly. Okay, so welcome Daniel and Eva.
Thank you. Thank you very much for this very nice introduction. Well, let me start. I will start and then I will pass the hard part to Daniel. That's the thing about being the first one. And well, I chose this rubber duck here with a little butterfly. And there is a reason for that you will discover. Well, this is joint work. To start with, I must say that this is joint work with Robert Cardona and Francisco Presas. This is contained, what we are explaining today is contained 3 papers. 2 of them are already on the archive, and the third of them will be on the archive soon, which is this XXXX. So this is the 4 little ducks who did this paper, the 4 of us, this class of papers. So let's start at the beginning. So what about putting a timesheet? So here you must think that maybe this guy here, who is Chris Moore, or this guy here, who you probably recognized already, who is Terry Tao, are the main characters of this talk. But this is not true. The main characters of this talk are these 2 rubber ducks, okay? Or, well, these 2 rubber ducks as a model of the 29,000 rubber ducks that were lost in the ocean in 92. So in 91, Moore asked in one of his papers if hydrodynamics was capable of performing computations. This is a quite strange formulation that should be clarified by the end of the talk. I will not address the computations part of this problem, but I will address a universality problem in my part of the talk, and then Daniel will talk about this understanding this question, is hydrodynamics capable of performing computations? Then let's go to the real deal, to our friends, these ducks. These 2 ducks are representative of the 29,000 rubber ducks lost in the ocean in January 92, because they were traveling from Hong Kong to somewhere in the States, and then there was a big storm, and then the ship just lost 29,000 rubber ducks. So what happened with these ducks are that these ducks started to appear in very strange parts of the world, and they have been used indeed, all the travel of these ducks, which was accidental, were used by people in oceanography already to know about the tides and to know about the tides indeed in the oceans. But well, here there is an important data. In 95, one of our collaborators who is fundamental for this work, Robert Cardona, and who is my PhD student who is connected there, he was born in May 17. So we will celebrate this probably with your thesis defense. And what happens is that in July 2007, one rubber duck shows up in Scotland. Okay, and somebody looked at this rubber duck and said, it's not possible that this rubber duck appeared here 14 years later. Okay, so our talk is about understanding if it's possible to determine if you throw, for instance, a duck, or if you throw a message in a bottle, if you like this kind of romantic films, and you throw a message in a bottle, you'd like to know if the person who you wrote this message for is going to get it. That's an important thing. If you send an email, usually this is most of the case what happens, this person gets the email. But if you send a message in a rubber duck or inside a bottle, what we prove is that it's not possible to decide if this person will get this is something we proved. It's not possible to decide if this person will get the bottle. Well, we prove this, there is a little trick. We prove this in 3 dimensions, not in 2 dimensions. If you think that these ducks move in 2 dimensions, then that's not the model that we are working. We are working with a 3-dimensional model. That's maybe the most exciting part of the talk, that I leave to Daniel. And this is something we proved very recently, just for Christmas in December 2020. We proved that there exists a Turing-complete Euler flow in dimension 3. And all these Turing machine stuff, in particular, one of the interesting things is that the halting problem is undecidable. In particular, this implies that if something is Turing complete, okay, then it's undecidable. So a nice corollary of this theorem that so far, I mean, we need to give definitions, but that is Turing complete, is that we prove that it's undecidable to find the little rubber ducks. Well, in the middle, before 2020, we have been working quite hard with Robert, with Fran, who I don't know if he's connected. Hello, Fran, if you're not connected and you see this in YouTube later, and with Daniel, who is here. We have been working quite hard. Indeed, we came to this problem of Turing completeness in quite an accidental way. Indeed, we were working on a different topic with Robert and Daniel, and then we came across a message in Twitter in which Tao was asking about universality of Euler flows. So universality of Euler flows, it's connected to the Turing completeness, but let's forget about the ducks and let's concentrate on the word universality. Universality, in very easy words, it means that he was asking if any dynamics, if given a dynamical system, if you can embed this dynamical system as some Euler flow. Okay, if you think about this question, it looks quite ridiculous because if you don't change the ambient manifold, the answer obviously is no. I mean, your dynamical system can be very strange, right? So why should it be an Euler flow? But the thing is that by universality, we mean that we embed this dynamical system in another higher dimensional manifold, okay? So that was the question that Tao was asking in his Twitter. Well, I don't know if it was his Twitter, but certainly we saw this on Twitter. And then at that moment, we were working with some interesting connections between Euler flows and contact topology, indeed with singular contact structures with Daniel and Robert. And this is how we started to work on this. Okay, so we proved a kind. Here I'm giving a very, very, very schematic statement. Okay, which is Euler flows are universal, but this means a very concrete thing that I will explain. And later on, we prove this Turing completeness. Okay, so that's the talk. The talk is about this. And so we lose this guy. And at the end of the talk, we prove that we cannot find it. So don't lose your rubber ducks. You will never find them again. Okay, so, okay, that's Daniel.
Yes, okay. Great, Eva. So good afternoon, everybody. So I'm going to introduce very briefly the Euler equations of hydrodynamics. So they describe, it's a system of partial differential equations, it's written here. They describe the evolution of a fluid flow, which is incompressible and has no viscosity, which means that it has no internal friction. And they make sense. They can be written on any Riemannian manifold of dimension n, mg. Oops, Eva, where did you go?
I was too quick, sorry.
Any Riemannian manifold, this is the system of equations. So there are two unknowns. One is x, capital X. This is the velocity field of the fluid, which is a non-autonomous vector field on the manifold. This first equation, it's the evolution equation for the velocity field. So you have the time derivative of x plus the second term, which is the covariant derivative of x along x, the covariant derivative computed with the Riemannian metric. And this must be equal to the gradient minus the gradient of another unknown of the problem, which is capital P, which is the pressure, the hydrodynamical or inner pressure of the fluid, which also depends on time. And then there is a second equation, which simply says that x is divergence free. So its flow preserves the volume of the manifold. Okay, so this is these are just the Euler equations that describe a fluid flow. But in this talk, we're going to focus on stationary solutions or steady fluid flows, Euler flows, which is the case when x doesn't depend on time. So in the Euler equation, the time derivative of x disappears. This is 0. So you get this equation that is written here. The covariant derivative of x along x is equal to minus the gradient of p. and the divergence of x is equal to 0. There is an equivalent, totally equivalent way of writing this equation, which is particularly useful when studying geometric problems or a geometric viewpoint of these equations, which is this one that is written here in terms of alpha. This alpha is the one form, dual to the vector field x using the metric, the Riemannian metric. And the equation simply says that if you take the exterior derivative of alpha, this is a two form, and you contract with x, the vector field x, then you get a one form. This must be this an exact form, which is it's what we call differential of b. B is the Bernoulli function, which is defined as the pressure plus 1/2 x squared. Okay, and divergence of x is always 0 because it's volume preserving vector fields. So there is a very special class, and you will understand this when Eva introduces the next slide, which is Beltrami fields. It's a particularly relevant class of solutions, of stationary solutions of Euler. They can be defined on any odd dimensional manifold, and they define in terms of a very important vector field in fluid mechanics, which is the vorticity. It's called the vorticity, this omega vector field here. And the definition is this that is written here. If you contract the vector field omega with mu, mu is the volume form, the Riemannian volume form, you get then a 2m form. Then this must be equal to m form, sorry, it's dimension m. This is equal to differential of alpha multiplied by itself m times. So you get again a 2m form here. And so you get a unique vector field that satisfies this equation because the volume form is non-degenerate. So with this way, you define the vorticity vector field, and a Beltrami field. Notice that this way of defining the vorticity is nonlinear as far as m is bigger than 1. So then a Beltrami field is simply defined as a vector field whose curl, whose vorticity is proportional to the field itself via some function f, smooth function, a factor. So omega is equal to fx, and the divergence of x is equal to 0. In the three-dimensional case, this is always a stationary solution of the Euler equation when m is equal to 1, and then the equation is linear. But for higher dimension, dimension 5 or higher, this is not necessarily the case. And actually, Robert, a student of Eva, as she mentioned before, he classified, or he studied, he characterized when these high dimensional Beltrami fields are stationary solutions of the Euler equation. And now Eva, I think, will introduce why these Beltrami fields are so important into this movie.
Thank you, Daniel. So now I'm going to take the same equations that Daniel introduced in the dual language, okay? And I dualize also the second equation. The divergence equation, you can also write it in these terms, where here, remember that alpha is the contraction of the metric with the vector field, okay? And mu is the volume form, okay, that he was mentioning. So the second equation that he was looking at, the divergence, we can write it like this, within the language of one forms. And here, let's say we have this kind of change of language, which looks like much more geometric to us, because we have these one forms all around. So, well, indeed, we can, well, one important, well, we have a one form. What can we do with this one form? Maybe we can compute the differential of this one form. Okay, and this is what we do here. If we compute the differential of the one form, okay, indeed, the equation, the first equation characterizes the Beltrami fields, where here we can think in dimension 3 that this is the curl. This proof is just for 3 dimensions, but it should work in general to introduce, well, here, then the equation is different. If we compute the differential, then what I want to say is that this equation, we can dualize it, and then it reads like this. Okay, the dual of the curl becomes, or the vorticity, it becomes the differential of alpha. Okay, and then this equation, the first Beltrami equation, can be written like this. And thanks to this, it's easy to see that if we take the differential of alpha and we wedge it with alpha, why would you like to do this? Well, it will become clear later, because this is a way to characterize a geometry associated to this one form, which is called contact form. Okay, so the first the condition for alpha to be a contact form in dimension 3, okay, higher dimension, the condition is different, is that alpha, which differential of alpha, never vanishes. And that's the first thing that you can check. And then associated to these one forms, there is a very special vector field whose dynamics has been of capital importance in the last 20 years, which is called the red vector field. The red vector field is it's given in the direction where it's in the kernel of the differential of alpha, and you can, of course, in the kernel of the differential of alpha, you have a lot of choices, and then you have to scale it, and you scale it so that alpha of x equals 1. So essentially, what we are saying here is that if we take these Beltrami fields, okay, in dimension 3, and if we consider alpha, the contraction of this vector field with the metric, then what happens is that we can associate to this alpha indeed a contact form, okay, maybe a different contact form by rescaling, such that the vector field that we are considering is, after rescaling, the red vector field of this contact structure. And this is like, the proof is very short. This idea, indeed, well, here I had to put a picture of Arnold, right? Because if you talk about Euler equations and you don't put a picture of Arnold, then you're lost. But the next one here, it's Sullivan. It's Dennis Sullivan, who indeed had this idea. Indeed, he has a collection of videos where this result is implicit, okay? And Daniel, I don't know if it's Daniel or Robert who passed me, I think it's Daniel who passed me this link, and it's very nice to follow a mini course that he gave many years ago, in which it was already implicit that this alpha was defining a contact structure. But indeed, who really proved this in full detail was Etnyre and Ghrist, who are pictured here. So they prove that there is a one-to-one correspondence between Beltrami fields and contact structures. Okay, so here the way to go is that if you have a Beltrami field, then you contract this Beltrami field with the metric, then what you obtain is a contact structure. But what may happen is that, and then the question is this the Beltrami field the red vector field with respect to this contact structure? Well, the condition of red vector field has two conditions. The first one, that it's in the kernel of the differential of alpha, and the second one is that alpha, which is a 1 form, against x equals 1. And of course, this condition, it's only satisfied if you take already a vector field of norm 1. So a different way to say it is that you can always reparameterize this vector, okay, to be so that you can reparameterize the red vector fields to get this vector. So there is a one-to-one correspondence between Beltrami fields and contact structures. And Etnyre and Ghrist already found several applications of this correspondence. So we may think that we have a kind of magic mirror, and that's a little bit the motivation. So we have a mirror or a glass, okay, and we want to look at the Euler flows through this glass and see if we can understand some new features of these Euler flows, okay? So here the glass or the mirror that we have here is the one, is this correspondence between contact structures and Beltrami vector fields. And the first application was obtained already by Etnyre and Ghrist, is that one of in the last 20 years or maybe 30 years or 40 years, already, yeah, 40 years since Einstein, 30 something years since Einstein conjectured that on any three-dimensional contact manifold, the red vector field had to have a periodic orbit if the manifold is compact. Okay, so that's the conjecture of Einstein. This was proved in a number of cases, including the three-dimensional case. And then they used this construction to prove the existence of periodic orbits for Beltrami vector fields in dimension 3. Okay, so what we are going to do today is to look again at this magic mirror, okay, and to ask a question to the mirror. And the formulation, this kind of duality that we have between Beltrami vector fields and contact structure, allows us to take techniques that are classical in contact geometry, like the H principle. Okay, and thanks to the H principle, we prove a kind of rep embedding theorem in contact geometry, if you want, that has as a consequence through the mirror, this indeed yields this universality of Euler flows. Okay, So that's a little bit the idea, indeed, the idea of the title. And we're going to do this again. We will look again. I will look at this magic mirror, and then soon somebody's calling me on the phone. I hope that everyone is listening. And can you hear me?
Yes.
Okay, thank you. Somebody decided to bother me calling on the phone. I thought it was Daniel telling me nobody can listen to you. Okay. Sorry for the interruption. Okay. I should have my phone next to me. Okay. So the talk, in this talk, we have two applications of this magic mirror principle. The first one will come via some H principle, which may sound as very complicated, sophisticated material, but I'll try just to give a hand-waving proof. And the second part will be really a constructive idea which is very simple to follow in contact geometry, which is like just doing a suspension, okay? And then this will have as an application this universality, this Turing completeness. So I'll take care of the universality. So I'm going to I put a slide because I said contact geometry, and I didn't have the right to do so because this is a dynamical system seminar. But okay, let me tell you in my defense that the red vector field and the study of the dynamics is something that pertains to dynamical systems. So to make myself to ask for forgiveness, let me recall what we are going to need in contact geometry indeed. I will, of course, recall some general result of Gromov. I will not prove it. I will do some hand-waving stuff, but what we need, which definitions do we need in contact geometry? Well, indeed, and in symplectic geometry. So symplectic and contact geometry have in common that they are the geometry associated to forms, okay? And in symplectic geometry, the form is a two-form, which is closed, non-degenerate, and non-degeneracy gives us a very interesting consequence that we can talk about Hamiltonian dynamics, because we can solve the equation in which I plug a vector field. I try to solve this equation, and this equation, I look at this is a two-form, and here I plug a vector field, and the vector field is what I don't know. And here I put the differential of a function. This is a one form, this is the known, and this is the unknown. And because of non-degeneracy, this has a unique solution. So whenever you give me a function, I can give you a vector field. And this vector field is called Hamiltonian vector field. And the dynamics of this vector field has already give as a consequence of the study of these dynamics is what we call Hamiltonian dynamics. And what about the odd dimensional causing of symplectic geometry? This will be contact geometry, which the dimension is always odd. And the geometry, instead of associated to a two form, is associated to a one form. And then the equation, which if you are in dimension 3, is the equation we were revising before, which was the proof of this one-to-one correspondence between contact and Beltrami. This gives me, in higher dimensions, then we have to wedge the differential of alpha to n, okay, and wedge it with alpha, and that the condition is that this is different from 0. And then, what are the dynamics induced on the manifold? Well, the first thing is the red dynamics. And indeed, there is also Hamiltonian dynamics, but today we will not focus on them. So I will not explain this second equation, but it's important to know that we can define Hamiltonian equations. And then in order to define Hamiltonian dynamics, we need to fix and to understand this direction, the direction of the red vector field, and to normalize it, okay? So the red vector field is the one which is in the kernel of the differential of alpha, okay? And then we take the one with measure 1. Okay, so that's all. Any questions so far? No questions, so, okay, good. That's the only thing we need to know about contact geometry. Well, that's not true. I will say, oh, Gromov said, and everyone will believe that he was right, but I will not explain. I will not need more definitions than this. So now let's talk about Tau's program for Universality of Euler flows. Okay. Indeed, the question that he posted in February 17 of 2017, Okay, so no, of 19, in February 17 of 2019, he asked if any incompressible vector field, so a vector field already satisfying that the divergence of the vector field is 0, can be embedded as an Euler flow by increasing the dimension of the manifold. He wrote a paper on this universality. Well, he wrote a couple of papers with this title, Universality of Euler flows, whatever. And so here is Tao writing his conjecture on the blackboard. And here we have some matrioskas. Okay, what are matrioskas doing here? Well, I bring DAX, matrioskas, whatever, so people keep attention. So indeed, the matrioskas are, the picture of the matrioskas is the idea that you have a doll, you open the doll, and you have a smaller version of the doll. Then you open again the doll, and you have a smaller version. And this can go forever. This is indeed an idea that is behind Tao's program, because indeed the question of universality is related to the question of constructing Turing complete fluid flows that we will see in the second part, the right definitions. And his motivation comes from Navier Stokes. Indeed, his motivation is to create an initial datum, which you can think of it as these matrioskas, that is programmed to evolve as a rescale version of itself. This is like a very sophisticated way to say it. I like the picture of matrioskas, but this is what John Moore would call self-replicating machines, in which you have copies and copies and copies. Okay, and his idea was to put these copies to generate some blow up in Navier Stokes. Okay, if he can do this, okay, then he gets $1 million, because this is a list in the Clay Millennium. We are not doing this to get this $1 million, because we know we won't get it, but this gives us a motivation to look these kind of problems. So the first question we want to ask is this question of Tao, and then the relation to Turing completeness will come later. I'm going to try to put a very some images to understand this idea of universality. Okay, so here you have a picture of any day in the winter in Barcelona, and this is a picture of any day in the winter of Madrid. Okay, well, okay, that's not always true, but I am the one explaining this slide, so I choose my pictures. So is there any difference between these two pictures? Well, maybe yes, maybe there are 7. Can you spot 7 differences? Well, of course you can spot more than 7, right? But the thing is that the idea of universality is that this can be your dynamics, and this can be a totally different dynamical system. Okay, but the idea is that if you are far away, you don't see this difference. So now imagine that you go to the outer space, okay, and you see from the distance Madrid is here, Barcelona is here, and they look the same. Okay, this is a picture from the ISS. Okay, so they all look the same. So that's a little bit the plastic idea of universality. And now let me give proper definitions first, but this is really the idea. The idea is that if you are far away, so if you increase the dimension of your manifold, you can embed any dynamics as Euler flows. So I need some dictionary. I need a short comprehensive dictionary to make things clear. We say that a vector field is Eulerizable. Okay, first I will talk about Eulerizable vector fields. I have a vector field on a manifold, and I say that it's Eulerizable. Here I don't change the manifold, but I can change the Riemannian metric. I say that this vector field, which I assumed it's autonomous, it's Eulerizable if there exists a Riemannian metric, okay, compatible with the volume form, such that this vector field satisfies the stationary Euler equations. Okay, so here, as you see, out of the many choices of Euler flows, we are fixing our attention in the solutions given by Beltrami vector fields, okay, or stationary Euler equations. Well, here I'm explaining the 3-dimensional case. This happens in any dimension, indeed. And one important feature is that this one-to-one correspondence between contact and Beltrami also happens in any dimension, with this generalization that Daniel explained. So the first definition is, what is an Eulerizable vector field? An Eulerizable vector field is a vector field for which you can choose a Riemannian metric such that this vector field indeed satisfies the stationary Euler equations with respect to this metric. Okay. Second definition that I will need, what is an Euler extendable vector field? An Euler extendable vector field, here I put the situation of considering a time periodic vector field, because then I get a compact extension. Okay, I could also consider non-time periodic, but let me considering now a non-Antonio, a time-dependent vector field, but I'm going to assume that this vector field is time periodic. Okay, and I take it, sorry, on a compact manifold. Then I say that it's Euler extendable if there exists an embedding, okay, on this manifold times S1 on a sphere of high enough dimension. Indeed, this is a sphere. This can be any manifold, any compact manifold. We take a sphere to make things a little bit more clear. Okay, so if we can embed this on a sphere, okay, and in such a way that we can, so we fix these time periodic vector fields. This is your dynamics, okay, and we say that it's Euler expandable if we can embed this dynamical system, okay, in a sphere, and in such a way that there is on this big sphere there is an Eulerizable flow, okay, so an Eulerizable vector field, so a vector field for which we can find a metric, okay, such that this vector field is the solution to the stationary Euler equations, okay? And what we impose, of course, is that this embedding, we impose that this embedding sends our initial vector field to this new Eulerizable flow. That's what this equation here is telling me, okay? And finally, the definition, what is our definition of universal? We say that Eulerizable vector fields are said universal if non-autonomous dynamics is Euler extendable. So if we can, by going far, far away, by increasing the dimension of your manifold, you can always find an Eulerizable flow such that your vector field is sent to this Eulerizable flow. Okay, so this is indeed putting some language to answer the question of tau. So the answer to the question of tau is this theorem, that this is what we proved in last year, no, 2 years ago already, in November 19, we have it on arXiv, where we prove that the Euler flows are universal, okay? And the dimension of the ambient space is, well, of course, it has to be a not integer, because here we play with this correspondence between Beltrami, okay, and contact, so it has to be odd, and depending on the dimension on n, so you take the smallest odd integer of these two integers here. One of them is going to be odd. Okay, so in the time periodic case, you can adjust the metric outside a ball, okay? So what you can prove is that the metric is a kind of perturbation of the canonical metric on Sn, okay? And GP, and this perturbation is really supported in a ball that contains the image, okay? So that's indeed a very complicated statement, but with words is to say that we increase the dimension of the manifold to embed the dynamics, whatever dynamics you give me, we embed it as solution of Euler flows. This looks quite shocking. How do you prove this? Well, by the way, a condition, well, a corollary of this result, since we talk about vector fields, we could also talk about the flow of vector fields. There is also the notion of having a diffeomorphism that it's Euler embeddable. Thinking of the idea of taking some Poincaré section and considering the flow of this vector field. And then, so this universality that we prove for vector fields, we can also prove for diffeomorphism. It's a concept. So I'm going to focus on the proof of this, and I'm going to prove this. I'm going to give the general ideas. How do you prove this? So we prove this, which is a question in dynamical systems, okay? By using, in order to do the proof, we need to look through this magic mirror between Beltrami and contact. So the correspondence that I was describing before between non-singular Beltrami vector fields and red vector fields reparametrized works in higher dimensions. This is not only exclusive for dimension 3. This is something that we can prove in any dimension. This is included in the proof is included in our paper. And what is known is that contact structures exhibit a lot of flexibility. And one of the features of flexibility is that you can put contact structure on manifolds that satisfy a minimal topological condition. This I will describe in a couple of slides. So indeed, the question that we were asking, can we realize a vector field as a red vector field on a bigger compact manifold, the condition that we need, geometrical condition, this is something that we proved, is that we need X to be geodesical. This condition of being geodesical, that is a condition that you learn in a school when you do differential geometry, but you learn it in a different language, okay? But it's equivalent to the existence of a one form such that alpha of X equal 1 and such that the constraint, such that X belongs to the kernel of the differential of alpha. This looks very close to the rep condition, okay? So is this condition sufficient? So let's say if we ask yourself the question, is a vector field, can this vector field be a rep vector field, which would be the equivalent to the contact mirror? Is this vector field, can this vector field be a Beltrami vector field? The first condition you need is the fact that this vector field is geodesical. So now we need to play some tricks. We need to play some dirty tricks from geometry, okay? And here we take as inspiration a theorem which was proved recently. This was proved in 17, okay, by Borman, Eliasberg, and Murphy, where they prove this thing that I said easy in words, which is that almost all manifolds, which are odd dimensional and satisfy a minimal topological constraint, admit a contact structure. This minimal topological constraint is called an almost contact manifold. So they prove that if the manifold is compact, here we say closed, we mean compact without boundary, that any almost contact manifold is compact. This is what they proved. And this is a generalization of former results. In dimension 3, this was known a long time ago by Martinez. In dimension 5, it took a lot of time to prove this. And this is a proof that has nothing to do with the general proof. It's different. Due to Fran and his student Roger Casals and Pancholi. Okay, so what is the philosophy of the H principle? So the inspiration, this idea of flexibility, this idea that you can move here, we have a vector field that is geodesical, okay? And what we want to do is to deform this vector field into a red vector field, because then through the mirror, I'll have a Beltrami vector field, and the Beltrami vector field is a solution, a stationary solution to the Euler fields, okay? So what is the H principle? The H principle is a magic, it's a magic idea, it's a philosophy if you want, which has three parts, as any philosophy. First one, it has a clear goal, which is we want to solve an equation. This equation can be a PDE, and more generally, it's called a partial differential relation, okay? And then there is a semi-goal, which is the thing you can do, which is solve what is called the formal equation, which is usually a linearization of your initial equation. If you're your PDE, it's a linearization of your initial equation. And the third thing is what we call the miracle. As any philosophy has some kind of miraculous part, the miracle is really that once you have solved the formal equation, okay, then what you wanted to do was to solve the initial equation. What you need to do is to connect somehow the solution of the formal, these linear solutions, or these linearized the solutions to the linear equation to the solutions of your initial equation. So you need to prove that there is some deformation or some homotopy that allows to deform the formal solution into an actual solution of the initial equation, which is called honest solution. Okay, and for that, well, for that there is no recipe. The important thing is that, well, you need to be lucky. And generally, if you have enough degrees of freedom, you can do this. And this is what people working in the H principle call that the system has enough high codimension or it's undetermined. So that's the idea of the H principle. And the idea of the H principle, we are going to apply it now. First, we're going to do a very hands-on proof. The first step is, as I said, that, well, using, this is something I have already expressed, so this is just a summary, using the correspondence between Beltrami flows and red vector fields, we reduce the problem of universality to universality of red flows. So we want to see if any vector field, by going far away, you can look at it as a red vector field. First condition you find the way, they had to be geodesical, okay? So the red vector flows are geodesical, okay? And then the other way around, the converse is true. What we prove is that any geodesical flow is rep extendable. Rep extendable, it's the same definition as I said. Okay. So what we proved initially, this proof is the easy one, okay, which indeed, this is indeed almost linear algebra proof. We can prove that because you write your equations, you want that this vector field is rep, and you allow yourself to increase the dimension. This is the same idea, okay, in Hamiltonian dynamics, okay, that you have a vector field and you want to have some kind of Hamiltonian dynamics associated to your initial dynamics. What do? Well, you take the cotangent bundle and you lift the cotangent bundle, and then out of the sudden, you had an initial dynamics that was not Hamiltonian, and you go to double the dimension, and you get exactly a Hamiltonian dynamics. So we play a similar trick, but we do it in the contact context. In the contact context, the equivalent to cotangent bundle would be the spherical bundle. Okay, so for that, indeed, if you think about it, you have your red vector field. For that, you need to go to dimension 2n minus 1 because it's the spherical cotangent bundle. So if you take the cotangent bundle, this is 2n, and then because it's a spherical, this is 2n minus 1. Okay, but you work with some kind of local models. You have an open manifold. Okay, and then this is one of the moments in the talk. Well, this is the only moment in the talk in which I'm going to ask Gromov for help. Okay, I'm going to ask Gromov, I have an open manifold dimension 2n minus 1. Can I embed this on a compact manifold? And he says, yes, you can do this. There is a theorem by Gromov, indeed done via the H principle. You can embed an open 2n minus 1 dimensional manifold on a manifold of dimension for dimension of n minus 1. And this is the proof. Indeed, what I have explained now is the proof of this theorem, that given a compact manifold and geodesical field, you can always embed this geodesical vector field as a red vector field on a higher dimensional manifold. Okay, and if you just apply Gromov, you have a manifold of dimension 4, dimension of n minus 1. Okay, well, if you're a serious person and you're working in dimension 3, well, this goes to dimension 11. You want something better. So you want to improve this bound here. Of course, here I have wrote a lot of statements, but this is the same through the contact mirror. Through the contact mirror, the representable condition tells you that if you have a geodesical vector field, you can always embed it as a Beltrami field. And this is wonderful because if your initial dynamics is geodesical, then it's already Euler. So you have already proved universality. Going to dimension 4, dimension of n minus 1. Natural question, can you do this better? You can do this better, and this is something we proved. This is going to be a black box in the talk, and I'm going to finish with this. Daniel, sorry, I'm going over time, which is that you can improve this bound by using the H principle. Okay, and this is a long part of the proof that we did, is to go from dimension 4, dimension of n minus 1, to dimension 3, dimension of n plus 2. Well, this is an improvement, because if you are in dimension 3, for instance, then this puts you in dimension 9. This is more reasonable than going to the previous bound. Okay, so sharpening the dimension implies using the H principle. So, okay, I'm going to put everything together, and this is my last slide. I have proved that any geodesical vector field can be embedded as a Beltrami vector field. I have done this looking at through the Beltrami mirror. The question is geodesical, and how do you know that your initial vector field is geodesical? How are you going to make your vector field geodesical? Very simple. You just take the suspension. So this is the lemma. So the lemma is you take your dynamics, you suspend it, okay? And then automatically the suspended, by increasing y dimension, well, this is a price to pay, your dynamics is automatically geodesical. Therefore, you just apply the previous extension, you plug, well, okay, you go to dimension, to this high dimension, dimension 3, to the one that is odd of these two here. So the smallest odd integer here, okay? And then you look at the, and that's your theorem. So your theorem is, no matter how your dynamics is, you can always embed it in one more to be geodesical, and then do the trick, this previous trick I explained, which is indeed linear algebra combined with the H principle, to prove the universality. Okay. And Danny, I'm sorry because I went over time. I'm done with my talk. I'm going to stop sharing.
Okay.
And questions towards the end of it. I'm sorry. I left you. Maybe now it's when we can ask for extra time.
Let's see.
I don't know when we started indeed. Alfonso with the...
I think you still have 15, 20 minutes maybe. We started a little bit late. So.
Okay.
So can you see now the screen?
Yes.
Yes.
Okay, very good. So yes, I'm sorry that we changed now because I was enjoying so much Eva's talk also, but it seems it's time now for the boring guy. So let's try to, to explain this. So now I'm going to introduce this second part, this second result that Eva mentioned at the beginning, which is about Turing completeness of fluid flow. So in short, what's the computational power of a fluid flow? Can we talk about a fluid computer in some sense? So for this, we need a definition. This definition here is not yet very precise. I will give you something more precise later. So we say that an Eulerizable field, in the sense that Eva defined before, is Turing complete if it can simulate any Turing machine. And how does this fluid flow simulate a Turing machine? Okay, roughly speaking, it's a relationship between the halting problem, the halting of a Turing machine with a given input, and the fact that a certain trajectory of the vector field starting at a point enters a certain open set. So this is essentially what we mean by simulation. So we will say that the Turing machine has some output if a certain point, if the trajectory at a certain point will reach an open set. I will give you a more precise definition, but for that I will need to introduce first the concept of Turing machine. And this is just a pictorial representation of a Turing machine with a tape. And here it's the equivalence that we want to establish between the dynamics of the Turing machine and the trajectories of the field, a point and an open set that we want to reach. Okay, so the theorem that we proved in this context is the following. So indeed there exists, and it's not only an existential result, it's constructive. You can construct, it's not easy, of course, but you can do it algorithmically. An Eulerizable flow on the 3-sphere, although the manifold, as Eva said, is not important, that is Turing complete. The metric for which this X is Euler is not the round metric, but it can be assumed to be the round metric in the complement of a certain embedded solid torus. And actually, the Turing machine, the universal Turing machine, is embedded in the solid torus, the dynamics. And outside the solid torus, actually, the dynamics of X is very simple. It's just periodic orbits. So you have a vector field on S3 on the 3-sphere, which is tangent to the Hopf vibration. But there is a part of the manifold which is a solid torus where the dynamics is more complicated, and the fluid computer is inside such a solid torus. A corollary of this, which is quite appealing, is that there exists undecidable fluid particle paths. So this means that there is no algorithm to decide whether a trajectory will enter an open set or not in finite time. You can understand this as a new or as another feature of complexity of fluid flows, which complements maybe chaos theory. This is related to this picture that Eva showed in the first slide, I think, which is the DAC, the DAC expresses the undecidability, and then the butterfly, which is the chaos effect. So it's a sort of different behavior. Chaos versus undecidability is totally different. And okay, there is a comment here about Navier Stokes, which is a consequence of this theorem, but I'm going to skip it. Okay, so just to be precise about these notions and about this theorem, I have to introduce the concept of Turing machine. So it's given by this set of objects. So you have Q. Q is a finite set of states, A, B, C, and D, for example. Q naught and Q halt are some particular states contained in capital Q. This is the initial state, and Q halt is the state that if you reach it, the machine halts. Sigma is the alphabet. Let's think of 0, 1, for example, a binary alphabet. And delta is the transition function, which gives you the evolution of the machine. And it's a function from q times sigma to q times sigma minus 1, 0, 1. This is just the shift to the left, shift to the right, or no shift, just the 0. And the input then of a Turing machine is the current state q and an infinite sequence of 0, 1s, which is this t, the current tape, which will evolve. So how does a Turing machine work? So if you have that the state is q halt, then nothing else has to be done. It's just the return, the machine returns the t, this infinite sequence of zeros and ones. Otherwise, if you have a state that is not the halt state, then you use the transition function. So you take the zero component here, zero element here of the tape. Then you compute the delta, and you get another q prime, and t prime naught. You replace q by q prime and t naught by t prime naught. So you have now a different shape with a different t naught here, t prime naught. And then you shift left or right or no shift at all. And you iterate this. And so the machine is, you have the infinite sequence of zeros, ones, 0, 1, you look, you check if it's halt or not. If it's not halt, you change the 0, you shift, you change the 0, you shift, etc. And this gives rise to the space of internal states, which is simply the space of states and all the tapes. Here you get a global transition function, which is this delta essentially acting on this space. And there is a notion which is quite relevant for us, although there won't be time to explain this in much detail, is the reversibility. That's important, the reversibility of the Turing machine, which is simply that the global transition function, or a certain extension of the global transition function, is injective. So now with this definition of Turing machine, is the usual one, of course, we can define very precisely what's the meaning of a vector field to be Turing complete. This vector field could be, for example, a stationary Euler flow. So we say that a vector field is Turing complete if we have this property for any integer k, any Turing machine t, and an input tape t, and a finite string of the output of symbols of the alphabet. There exists an explicitly constructible point of the manifold and an open set U, such that the orbit of this vector field of x through the point P intersects U if and only if, now this is the connection with the Turing machine, T holds with an output, which is this T star. So you have the equivalence. And this is how the fluid is computing, because you relate the tape and the output to a point of the fluid, an open set of the fluid, and then the evolution it's given essentially by the flow of the vector field, right? So now just a remark very briefly, I don't want to spend much time on this, is that it's not true that there are some wrong intuitions and there are some parts in the literature which are quite misleading, which say that the usual shift dynamics is Turing complete. This is not the case, because okay, to understand this as Turing complete, you need to take all the initial information at the same time, which is an undecidable problem. So the moral is that you need something else to construct a dynamical system that is Turing complete, and this is where Chris Moore appeared 30 years ago, and he generalized the notion of shift to simulate any Turing machine, and in particular to simulate a universal Turing machine. So this is a concept of generalized shift. So generalized shift, so if you take an alphabet, let's say 0 and 1, a generalized shift is a map from the power AZ to AZ, this infinite sequence of 0 1s, is specified by two maps. In the case of the usual shift, the map G is the identity, and the map F is just +1 or -1, depending if it's shift to the left or shift to the right. And the functions F and G depend on a finite number, on a finite amount of elements, of positions in the tape, let's say in this A set. And so G is just given, it's just a function which takes you, takes L elements here in AL and gives you other L elements. And a function F gives you just an integer number. So the generalized shift is simply, so you take an S, the infinite sequence of 0 1s, you compute F on S and G of S, which depend just on a finite number of positions of this infinite sequence. Now you modify your sequence, changing the positions, these positions here by G of S, by the image of S by G. You get another S prime and another sequence of 0 1s, and now you shift how many or how much you shift this Fs times Fs positions, because F is an integer. So this is a generalized shift. And as I said, if G is the identity, you change nothing. And if F is +1 or -1, shift to left, shift to right. This is just the standard shift in dynamics. Okay, so the important lemma of Moore is that one of the important lemmas of Moore is that any Turing machine can be simulated or is conjugated in some sense to a generalized shift. So we can understand or we can study Turing machines using generalized shifts, which is quite convenient from the dynamical viewpoint, because you have these dynamics provided by the generalized shift, and you can conjugate, or you can understand these dynamics in the same way as the dynamics of the shift can be understood as a dynamics on the square Cantor set, right? The ternary square Cantor set. You can understand this as a map of the square Cantor set into itself. And for that, the only thing you need is some point assignment. How, if you have a point, if you have an infinite sequence of 0 1s, this S -1, 0, what's the corresponding point in the Cantor set, in the square Cantor set? It's, well, this is just the usual, I think, point assignment, which is expressed this way. So you have two coordinates, X and Y. It's a point in the plane. So the Y coordinate, it's expressed in base 3. So it's just a sequence of zeros, 0, 1, or 2, but it's just zeros or 2s, depending on whether the corresponding position here is 0 or 1. And this is in base 3. This means that this is y naught times 3 minus 1 plus y1 times 3 minus 2, etc. It's always a number smaller than 1, because this is the square Cantor set is contained in 0, 1. And all the same for the x component. So you get assigned to each point, you have a bijection, assigned to each point, to each element of the sequence, you have an element of the square Cantor set. And now the very nice observation result of Moore is that any generalized shift is conjugated to the restriction to the square Cantor set of a piecewise linear map of the square. There is here a pictorial representation, which is easier to understand. So you have, depending on the generalized shift that you want to simulate with a map of the square Cantor set, you have a number of components here, of blocks. Here it's 4, for example. And Moore says that any generalized shift, which is a map from the square Cantor set to itself, there is a piecewise linear map, in this case of these 4 components, whose images are these A prime, B prime, C prime, such that the restriction to the square Cantor set is precisely conjugated to the generalized shift. And there is the very important property, although there is no time to explain why, that if the generalized shift is bijective, which is related to the injectivity of this, or to the reversibility of the Turing machine that is representing, then the image blocks are pairwise disjoint. And this is very important, because it allowed us to prove the following key result, which is that for any bijective generalized shift and its associative map of the square Cantor set, there exists an area-preserving diffeomorphism of the disk, which is the identity in a neighborhood of the boundary. This is just a technical condition, not really necessary, but okay. it makes life easier to assume this, whose restriction to the square Cantor set is conjugated to the phi. So in short, you can embed the dynamics of any generalized bijective generalized shift into the dynamics of an invariant set of a diffeomorphism of the disk. Okay, an invariant set which is a square Cantor set. And okay, there is no time to talk about the proof, but it's essentially extending somehow Moore's piecewise linear map and elaborating to be able to transform this into a diffeomorphism that preserves area, which is not immediate from Moore's construction. Okay, so now we are ready to prove this result. So if we take a reversible universal Turing machine and its conjugated generalized shift, we said that any Turing machine is conjugated to a generalized shift, then we prove this result, which is that there exists area preserving diffeomorphisms of the disk that are Turing complete in the same sense that I specified, that I told you before. Given any Turing machine, any input, any output, the evolution or the halting of this Turing machine is related to a point reaching by the iteration of the diffeomorphism as a certain open set. This is the notion, this is the result. And just a remark, 1 minute remark here, which is quite important, is that this is not robust. Not robust in the sense that if you perturb this diffeomorphism, area preserving diffeomorphism of the disk, Turing complete, being able to simulate any Turing machine, it loses its computational power. Okay, it's related to the compactness of the example. Okay, so now we are ready to tell you the sketch of the proof of the result of the fact that there exists a steady Euler flow which is Turing complete. So a first key step is the mirror that Eva explained, the Beltrami contact Beltrami mirror correspondence, which allows us to reduce the problem to establishing universality, to establishing Turing completeness of a rep flow. So for this, we need this embedding theorem. The embedding theorem says that if you have a diffeomorphism of the disk, area preserving diffeomorphism, the identity in a neighborhood of the boundary to make life easier, then this can be embedded as the Poincaré map of some rep vector field on the manifold. So there exists a defining contact form whose associated rep vector field has a Poincaré section whose first return map is conjugated to this phi. Okay, so with this, if you take that your manifold is F3, for example, that is not really important, and you take the standard contact structure, you take the Turing complete diffeomorphism we constructed here, you embed the diffeomorphism as the Poincaré map of a rep flow, of a rep vector field, and you use the Beltrami correspondence, so you get an stationary Euler flow for some metric, which is actually, since this diffeomorphism is the identity on the boundary, you are able to fix the contact form to be the standard contact form in the complement of a certain solid torus. This will ensure that your vector field is circular outside the solid torus, and this proves the second theorem, the theorem of the Turing completeness of stationary Euler flows. Okay, so now there is this last remark, this spoiler. So it's up to now we just talked about time-independent stationary solutions, right? So it's so the vector field doesn't depend on time; it's autonomous. So what about considering the flow with quotations? Because Eva mentioned the blow-up problem. It's not known if the Euler equations define a global solution given an initial datum. Is it possible to say something about time-dependent solutions, about this infinite dimensional flow for some manifold, at least? So for this, we have an analogous definition of Turing completeness of the Euler equations on a manifold. So given any Turing machine, any input tape, any output, part of the output, and we talk about Turing completeness, if there exists, now the initial point now is not a point on a manifold, it's a point in the infinite dimensional space, so it's a vector field. It's x naught, which is a volume preserving vector field. That's the initial datum of the Euler equations, right? A vector field, a velocity field, and an open set in the space of infinite dimensional of divergence-free vector fields, open in the C-infinity topology, for example, such that the solution to the Euler equations with this initial datum is smooth for all time and intersects this open set U if and only if T halts with a certain output. So it's exactly the same finite dimensional definition, but in the infinite dimensional phase space, if you want, of the Euler equation, which is the space of divergence-free vector fields. So the theorem that we established very, very recently, and even it's not yet in the archive, but it will be soon, in a few days, it's that indeed there exists a compact Riemannian manifold, MG, such that the Euler equations, time-dependent Euler equations, are Turing complete. So in this sense, which in particular implies that if you have an initial datum, an initial velocity field for the Euler equations, you cannot, there is no algorithm, you cannot decide whether it will reach a certain open set in the phase space of the fluid flow. If we'll reach some other open set here in the space of infinite dimensional vector field. So you have this as a complement to the complexity of behavior of time-dependent fluid flows. Okay, and I think that's all. Maybe Eva wants to add something at this moment, but if not, thank you for your attention.
Thank you.
Thank you. I clap. Thank you for this very nice talk. So, time for questions. So, is there any comment or question? So, okay. So, actually, I have some, first of all, some clarification about the definition of universality. When you say that the Euler flow is universal, so do you mean that for any dynamical systems, so there is a common ambient manifold Sn, so the dimension is the same for all?
I mean, the manifold that you construct depends on the dimension of the ambient manifold of your initial dynamical system.
You know what I'm saying is that in the embedding, you embed in this Sn.
Yes.
So the n has to be the same for all possible autonomous dynamical, non-autonomous dynamical.
No. This n. Yeah, this is what I'm saying. This depends on the dimension of n.
Okay.
So there are two n's. So you have your initial system, dynamical system, on a manifold dimension, which I call n, or let's call it m. Okay. Then you have this Sn. Then the dimension n depends on the dimension of your initial manifold.
Okay, but it's the same for all dynamical systems.
You can find. Well, this is something I excluded. There is some kind of universality more proof that I excluded from the proof. There is something that I wanted to say in it when you said that I wanted to add something else. I mean, to link both parts of the talks, that initially, one of the consequences of universality, the one is the corollary, which I should have indeed included, and I didn't because there were too many things, is that as a consequence of universality, because you can get, we were getting some Turing completeness on a sphere of dimension 17. This is important to connect both parts of the talks, because we were using some construction from Tao, where he was taking a T4 on a 4 torus, and then I was doing the geodesic trick of putting it this, and then embedding things in dimension 17. And what I wanted to add is that what we did later, and what Daniel has been explaining, the greatest comes as a consequence of this other proof. But, well, comes as a consequence, not comes as a consequence. I mean, it was a natural question. Can we go to dimension 3? And that was the point. So as a consequence of the proof of universality, we were getting Turing completeness in dimension 17. Okay. And then I was telling this to a colleague in my department whose name is Cabrera, and he was laughing. He was saying, what I'm going to do in dimension 17. And that's not related to your question, but this is something I want to say. Okay. And related to your question, you have this dependence. I mean, we have some universality construction it's possible to improve this universality construction. But I think I don't want to add more information.
Yeah, sure. No, but then
I think we added too many things in this talk.
Okay. But then the question, another question, and related one, once I understand better the definition is, so you have this embedding for a non-autonomous flow. I guess it's not unique.
Yeah.
Can you say something about how many, or what is, I mean?
Yeah, that's a good question. Indeed, because you can use, so once you have one embedding, then you are, I mean, once you cross the mirror and you are in contact geometry, then any kind of questions of, you can formulate them in contact geometry. And that's an interesting question. And then in contact geometry, you realize that you can essentially, and that's a natural question, how many contact structures can you have? Can you deform it? Can you deform them? We didn't, I mean, let's say, indeed, let me think. Indeed, I mean, let's say our proof, I mean, there are like two questions here. You could get a different contact manifold, or you could get a contact manifold following our recipe. Following our recipe, you can deform things, but I don't know in general. I mean, well, this is a question for contact topologists. Where is Frank?
Maybe can I say something?
Yes, of course. I mean, and a question for the student.
Right, so about the question of Alfonso, so the improved theorem, which uses H principle, actually tells you that if the dimension is higher than something, then any smooth embedding can be perturbed to be a rep embedding, and it's a C0 closed perturbation or something like this.
Yeah, that's true.
So these embeddings exist, let's say, in abundance, you know?
So it can be perturbed in which topology? In
C0.
Yeah, that's true.
Oh, nice.
That's the theorem. Well, that's one of the theorems we didn't show. Yeah, that's true. We have this C0. That this comes from another proof. Indeed, this comes from the proof of the fact that any manifold admits a contact structure if it's almost contact. It's almost contact, it's a kind of topological thing. If it satisfies this topological condition, then it admits this. And then indeed, what we did was to essentially take the H principle that they use, and then in this H principle, you have exactly this condition that Robert is telling. But I didn't show this theorem, and I didn't want to get very far because indeed, well, we did this 2 years ago and we were not very successful with this result, but let's say we were more successful with the three-dimensional construction that Daniel explained, which is...
Okay. So, thank you. Any other comments?
Which was supposed to be the character, the main character of the talk, but because it's my fault that I don't know. I didn't have my phone next to me, that's first of all, and then I got overexcited, and then Daniel didn't have time to talk why you cannot find the same duck. So don't lose your ducks because you will never find them.
We'll invite you for a second talk then. So other questions or comments?
So I may say something funny, which is, so if you believe that dimension 17 is high, this dimension 17 that Eva mentioned, don't ask, please, about the dimension of the manifold of this spoiler theorem. That
the spoiler, you should
this
say
very
it.
last
this
theorem
dimension has changed in the last 24 hours.
Because
we have a paper and yesterday we went from dimension an estimate of 10 to 33 to 10 to 35.
Okay.
But it's very cool. I think it's a very cool construction. But we didn't, I mean, we're going to post it probably on Monday or tomorrow. I don't know. It's probably on Monday will be online.
Okay. So comments or questions? So if not, let's thank Daniel and Eva again for the very nice talk. High clap for everybody.